Have you ever wondered what the secret is for engineers building these massive global scale systems at places like Google or Amazon? Well, a big part of it is a skill that feels almost like a superpower, back of the envelope estimation. It's a way of thinking that lets you make incredibly smart, fast decisions about system design way before you ever write a single line of code. So let's dive in and see how it works.
So first off, why should you even care about this? Well, this quote pretty much says it all. Just 100 milliseconds, literally the blink of an eye, was costing Amazon 1% of their sales. Now think about what that means today. We're talking billions of dollars. This isn't just about a website feeling a tiny bit sluggish. This is about a direct, absolutely massive impact on the business.
And that really gets to the heart of it. When you're working at scale, performance isn't just some nice-to-have feature you bolt on at the end. It is the product. If it's slow, you lose users. You lose money, period. So the real question becomes, how do you even begin to design systems that can handle millions of users without just falling over? How can you predict those costly delays before they ever happen? Well, the answer is a technique that's really more of an art than a science, but it's one that is absolutely critical for getting it right. It's the secret that lets engineers get a quick reality check on a design to see if it's even viable without getting completely lost in the weeds of complex calculations.
And this is what we're talking about. Look, the key here is not about getting a perfect calculator-precise answer. It's all about using a few common-sense numbers to ask the big questions. Will this design work for 1,000 people? What about 10 million? This kind of quick math gives you that essential gut check, and it gives it to you fast.
The best way to think of it is like a mental toolkit. And today, we're going to unpack the two most important tools you need in that kit. First, a real sense of data scale. And second, an almost intuitive grasp of just how fast and, more importantly, how slow different parts of a computer really are. All right, first up, let's get a handle on just how big data can get. We throw around words like petabytes all the time, but what does that actually mean? Having a solid mental picture for these powers of two is pretty much the foundation for any kind of capacity planning. Now, we've all seen these terms a million times, but the thing that's truly critical is to internalize the sheer size of the jump between each step. Each one is roughly 1,000 times bigger than the last. A gigabyte might hold a movie or two. A terabyte can hold hundreds. A petabyte, you could probably store the entire Netflix library multiple times over. When you're trying to estimate storage, knowing if you're in the gigabyte world or the terabyte world changes everything. It's the difference between needing a bookshelf and needing to build a whole library. Okay, now for the second tool. And honestly, this is where things get really interesting. This is all about understanding the true speed of your computer. And I promise you, these numbers are probably going to surprise you. They completely change how you think about writing code and designing systems.
So let me ask you that question. How fast is your computer, really? We think of them as being lightning fast, and in many ways they are. But not all computer operations are created equal, not even close. Some are so unimaginably faster than others that it's almost hard to comprehend. Let's take a look.
Let's start with the fastest of the fast, accessing the L1 cache right on the processor. This takes about 1 nanosecond. Now, to put that in perspective, 1 nanosecond is to 1 second, what 1 second is to nearly 32 years. It's basically instantaneous. This is like reaching for a book that's sitting right on your desk. Okay, what about main memory, your RAM? That takes around 100 nanoseconds. Now that's still incredibly fast, but it's 100 times slower than the cache. In our little analogy, this is like having to get up from your desk and walk over to a bookshelf in the same room. It's a noticeable difference.
All right, get ready for a huge leap. What about reading data from a modern SSD? That's going to take you about 100 microseconds. A microsecond is 1,000 nanoseconds. So we just went from 100 nanoseconds for RAM to 100,000 nanoseconds for the SSD. We're not walking across the room anymore. Now we have to go down the street to the local library to get our book.
But here it is, the biggest jump of them all, a round-trip network call. Let's say sending a tiny packet of data from California to the Netherlands and back again. That's about 100 milliseconds. A millisecond is 1,000 microseconds. So we just jumped from 100,000 nanoseconds for the SSD read to 100 million nanoseconds for that network call. This is no longer going to the library. This is getting on a plane and flying to another continent to get your book.
And just look at this chart. It puts everything into perspective. If the time it takes to get something from the cache or even from RAM is the thickness of a piece of paper on the floor, then the network trip is a skyscraper. The difference isn't just big, it's astronomical.
And understanding this visual right here is probably the single most important concept in all of performance engineering.
So what does all of this boil down to? It's actually really simple. Memory is fast, disk is slow, and the network is really, really slow. Every single time your application has to go across the network to get something, you are paying a massive, massive performance tax. And going between data centers, that's the most expensive trip of all. This one insight drives almost every major system design decision out there.
Okay, so we've got our two tools, right? We have a sense for data scale, and we have these mind-blowing latency numbers. So, how do we actually put them to work? Well, it's all about adopting the right mindset.
And it really just comes down to 3 simple rules. First, round your numbers a lot. Be aggressive. We're not doing calculus here. We're just trying to see the rough shape of the problem. Second, always, always state your assumptions. This isn't about being wrong. It's about being clear so people can follow your thinking. And finally, for the love of all that is holy, label your units. Mixing up kilobytes and megabytes will make your estimate off by a factor of 1,000.
And this right here is the core philosophy of the whole thing. The goal is not to predict your exact server costs down to the penny. The goal is to figure out if you're going to need 10 servers or 100 servers or maybe 1,000 servers. It's all about understanding the order of magnitude, about just being in the right ballpark.
So when you put these two things together, that feel for data scale and that deep appreciation for latency, you start to see the future. You can spot the bottlenecks in a system before it's even built. You can make smarter trade-offs, and you can design systems that are built for speed from day one. And that is the power of back-of-the-envelope estimation.